Hello, everyone. Welcome to my IVF Answers webinar platform, part of the European Fertility Society, which is dedicated to supporting, raising awareness, and educating patients who are facing infertility challenges. The European Fertility Society core mission is to guide and assist patients in making one of the most significant decisions of their lives, choosing the right fertility treatment solutions, as well as ask questions live, like on today's event. Today, we are starting an exciting series of events dedicated to mitochondrial replacement therapies, MRT, which will be addressed from various perspectives, featuring experts from around the world. And we plan to perform 8 events in that series. So it is with real pleasure to start the series here with Birol Aydin, Laboratory and Scientific Director of Ovogene. He is a consultant at the International Fertility Group, and he is also an ESHRE certified senior clinical embryologist. He has more than 15 years of working experience in embryology and andrology, worked in more than 20 different countries, and he has performed over 30,000 IVF and ICSI cycles in his career. Before I hand over to Birol, just to remind you that the event is being recorded. It is all anonymous, and the recording will be available the next day, tomorrow, on our platform on the YouTube channel as well. We will start with the presentation when I hand over to Viral, and then we will follow with the question and answer questions session as will follow. Now I want to go ahead with our presentation, and over to you, Viral, when you are ready, please.
Okay, I will just share the presentation now. So first of all, welcome everyone. It's a real pleasure to be here. With most of you, actually, we are talking with a different platform. We are discussing, we are trying to understand how the process protocol is working. But of course, this is for me a good chance to be all together and to share all details regarding mitochondrial transfer to understand so for whom these techniques we can use effectively and how we get from this technology the maximum benefits for patients. So the first of all, we have to understand what is the role of mitochondria. Firstly, mitochondria is the energy source of the cells. So mitochondria can pass from mother to child and contains 37 genes. Most of the genes are connected mostly with immunological part. They are not directly affecting your chromosomal structure, or they are not decision maker or general gene profile. But of course, the mitochondria has importance. So mitochondria is supplying energy to whole cell mechanism. And of course, mitochondrial mutation, if you have it, so it can lead to fatal inherited diseases, which is mostly there is no any cure or treatment except mitochondrial transfer. So when we try to understand mitochondria, so we have to know mitochondria is energy supplier, which we are calling ATP energy. This is energy which can send through mitochondria to your nuclear DNA and feed your nuclear DNA with the intracellular energy. That's why how your embryos are developing, and the morphological and morphokinetic development is getting better depending of quality of this energy. There are two main organelles over there, endoplasmic reticulum and mitochondria. So endoplasmic reticulum produces calcium. Calcium is coming with their channels to mitochondria and just carrying up the energy and transporting directly to your nuclear DNA, and your nuclear DNA is feeding and getting enough amount of energy and creating all structural and chromosomal development. So here we have to understand that mitochondria has one side in energy roles, but on another side also is joining DNA composition. That's why 99% of the mitochondrial DNA is inherited from the mother. So there are critical diseases which can carry up by mitochondrial DNA as well. of course, the biggest question here, how we will know that we have mitochondrial diseases. It's not so easy because there are so many genes which can be connected with the mitochondrial diseases. So mostly how patient aware that once they have child, which is affected with the mitochondrial mutations, so they find out, and this is the way how they are aware from the mitochondrial dysfunction. So this is actually the critical issue. But once they have this mitochondrial mutation report, of course, through mitochondrial transfer, if we change the mitochondrial DNA source, we can solve this issue for the next generations. So, what is the connection mitochondrial mutation with advanced maternal age? So, once I started to work for mitochondrial transfer, it was almost 10 years ago, which started with the somatic cell transfer, which we were working only for potential gene mutation and diseases. And it was mostly on the stem cell stage. But once we start to work for mitochondrial disease, and mostly that who had mitochondrial mutation or disease, those patients were over age. Now, when I say over age, I'm talking about the biological age, like advanced maternal age, over 38, 40 years old. So we find out, yeah, we can treat it mitochondrial mutation from one side, but on another side, normally we have expectation from those group of patients, low morphological development, low blastocyst rate, or high aneuploidy rate. But we find out that patients are reacting so good, that embryos are developing much better. We are receiving more blastocysts. And then the question comes, what if we do that technology and if we use that technology for advanced maternal age? So for the advanced maternal age, the most critical things about the mitochondrial DNA, one part of microdeletion. So this microdeletion directly affecting the fertilization and blastocyst outcome. So this is the critical part. Once we change mitochondrial DNA, of course, we are treating this part and embryo are developing much better morphokinetically. Uh, Also, here is a question. Of course, embryo aneuploidy is increasing through advanced maternal age. And this is mostly happening in the meiotic division, one or two. And during the mitotic error, of course, embryonic cleavage division has affecting, and mostly embryos are getting cleavage arrest. So most of the advanced maternal age patient, they have till day 3 good quality of embryos, but then finally they cannot receive either on day 5 or day 6 blastocyst, or they receive a very low quality blastocyst, or it end up with aneuploidy. So here, of course, next slides we will talk if mitochondrial transfer also is a good alternative for aneuploidy. But of course, as a main idea, mitochondrial transfer doesn't support euploidy or aneuploidy. The mitochondrial transfer mostly focus on morphokinetic development of the embryo because of the energy source. So during advanced maternal age, what is happening in body? Mostly an oocyte stage problem is occurring. Of course, lower fertility, so increased implantation failure, the increased miscarriage rates, also congenital anomalies are increasing because of the mitochondrial dysfunction, because structure of the mitochondria is changing. The mitochondrial DNA mutations are increasing, ATP production as energy source decrease, and also mitochondrial DNA copy number of mitochondrial DNA is getting lower. So all these effects is giving to embryo low development, or it's affecting the euploidy rate, and aneuploidy rate is increasing dramatically on the embryo for advanced maternal age. As from one side, for advanced maternal age, of course, we are expecting low quality of the oocyte and low number of the oocyte. But it's not just typically for advanced maternal age. Same situation we can find out for polycystic ovary syndrome as a PCO cases. For PCO cases, we have big number of oocytes, but with a very low quality, which has some spindle, which is carrying up 99% female DNA. So some spindle dysfunction, also centromere dysfunction, and also the morphokinetic development through embryo development. So those cases as a polycystic ovary syndrome also actually can get benefit from mitochondrial transfer in case if they don't have from several IVF trial any blastocyst or high quality of the blastocyst. So how this aneuploidy issue actually occurring and what we can do for aneuploidy issue for the mitochondrial transfer. So mostly when oocytes start to develop for advanced maternal age, from one side, oocyte developing morphologically with the low quality, they have some cytoplasmic abnormality as a shape of oocytes mostly looking abnormal. They look very fragile, as for microscopic way. They have not high quality of zona pellucida, which we are calling wall of the oocyte, and the polar body, which is carrying up the nuclear DNA, and also there's some morphological abnormality on the polar body. So especially on the metaphase 2 stage, of course, which is spindle, meiotic spindle formation is occurring, there is some issue happening for the chromosomal structure. So that's why when we talk about the mitochondrial transfer, we are talking about different techniques as pronuclear transfer and meiotic spindle transfer. So meiotic spindle transfer can be here one option as limited number of chromosomal structures we can get benefit. Especially most of patient, advanced maternal age patient, they have high mosaic embryos, over 60%, some monosome issue, and those chromosomal structure problems can be detected and solved by early metaphase stage of the oocyte development. That's why we are using as a meiotic spindle transfer as an advance to help not just for the morphokinetic development, also chromosomal composition and chromosomal structure. But of course, again, this is an individual, so every of you has a different aneuploidy issues. So if you have, I'm saying as a trisomy issue, that means you are receiving that repeated failure on the aneuploidy testing as 13, 18, 21, the main chromosomes, so which they are carrying up multiple aneuploidies, chromosomal aneuploidies. Of course, this is your pure nuclear DNA. Even on the early metaphase stage, we cannot solve these issues because these are coming from very early stage during follicular development. But still, like there is a rule in every cell, not just for the egg, sperm, or embryo, but every cell. So if some cells developing morphokinetically better, so they can build their self-repair mechanism, and this is intracellular mechanism which we cannot exactly understand perfectly how the mechanism is working, but it's a kind of like if we cut our hands, so my hands can repair itself in maybe one day, but some another for 2-3 days. So it's for every individual cells also showing different reaction. That's why we have different euploidy, aneuploidy rate, even for advanced maternal age. The patient can come with 46 years old with 5 embryos, and even all of them can come euploid, and patient can come with 32 years old and all embryos can come aneuploid. Even I have example with more than 10 blastocysts, all of them coming aneuploid. So this is still possible. So it's again on the intracellular stage, and so it's not so easy to detect and find out what is the reason of the aneuploidy. But of course, if patient have history of PGT testing, so that's giving us some information exactly if mitochondrial transfer can be helpful or not. So this is only for the genetical stage. So for the advanced maternal age, also we have to see here as a number of euploid blastocysts comparing aneuploid blastocysts, of course, very low. So it is mostly all publications or journals, all scientists and different clinics, when they publish their euploid rate, you will see over 35 years old, you will find out aneuploid rate increasing to 60% to 70%. So this is mostly connected, of course, with the age, biological age, but also mostly connected with the morphokinetic development of the embryos. The same issue for the number of blastocysts. So in the younger age group, of course, there are high blastocyst rate with the high mitochondrial DNA quality, but for advanced maternal age, this mitochondrial DNA quality is getting lower, and directly also blastocyst rate is getting lower. So also that publications are supporting mitochondrial DNA quality and the blastocyst quality is compatible. So as mitochondrial replacement therapy, you will find when you try to search on internet on different journals, so you will find out with a different name as a three-parent IVF, three-person IVF, so mitochondrial replacement, or mitochondrial gene replacement. So some of them right, some of them not. Actually, like they are calling three-parent IVF because three different genes have involvement here, but actually, like, not amount of the mitochondrial DNA or amount of the nuclear DNA, let's say, it's coming from the couple who supply the egg and sperm, almost 99%. So that's why I don't prefer to call actually three-parent or three-person IVF, but we can call the right way as a mitochondrial replacement technique. So this is the most clear and easy way. So how this energy happening in the intracellular mechanism. So this video shows how mitochondria is giving energy, and when mitochondria give energy to cells, how cells showing reaction to this energy. So you will see here, once calcium bring with the channels the energy, how that oocyte and nuclear DNA will give reaction to that. Did you see? So the first one, there is no first video, there is no active mitochondrial DNA over there, and it's not working. That's why first oocyte didn't get any energy supply, but second and third one has active mitochondrial DNA. Even in third one, as you see, the color of the eggs totally changed because it complete with a high amount of the mitochondrial energy and ATP energy. So this is how cellular mechanism is working better. So as we talk about the euploidy, aneuploidy, because this is the one of the big problem for advanced maternal age, except blastocyst development. So if self-correction mechanism in embryos are working, and what we know about it. So here, that is DNA. There are different kind of DNA damage, of course, with a different reason, for the oxidative stress, for the mismatch, or during the first stage of mitosis, some kind of chain break on the DNA. Of course, the main point is apoptosis here. So apoptosis means is a programmed cell death. That means in any part of your body, there are different type of cells, and those cells are getting older because every cell has lifetime. So when those cells get older, they should actually die, and the body should produce, or different organs should produce, new cells, the fresh young cells, and they should take place of old cells, and old cells should thrown away. But on advanced maternal age, while we are getting older, so this mechanism is getting interruption. We are receiving old cells, we cannot produce new cells, and those old cells getting more and more and making barrier. This is same as in the follicular stage, same as on the endometrium. That's why every of your follicle, even you can count 20 of the follicles on advanced maternal age, but finally you are receiving 5, 6 oocyte, even for good amount, good size of the follicles, which is 17-21 millimeter, but they are not supplying your oocytes. So the partially it is the metabolic mechanism through apoptosis, how it is happening. So that's why I said here repair mechanism can work, because if we can solve apoptosis issue with external technologies while we are giving higher mitochondrial energy, that means we are renewing apoptosis mechanism, and we are believing with this mechanism we can also activate intracellular repair mechanism. So meiotic spindle, which carry up, as I said, 99% of the female DNA, and the 1%, of course, is the mitochondrial DNA. This is total composition of the DNA. So meiotic spindle is very important role, firstly for the chromosome separation and the fertilization, and also activation of the second polar body, which means that those oocyte is fertilized and completed meiosis two stage. So the quality of the meiotic spindle, it's directly influence blastocyst outcome, embryo potential for the implantation. So as meiotic spindle transfer, how it works? So we are using that intended parent X, like a female X, we determine with a polarizer the location of the spindle. We just take it this spindle. So this is our target spindle, which we need to use for mitochondrial transfer. Then same time, we are selecting high quality donor X as a morphological, but not just a morphological, also from the efficiency part. So donor X and donor should be very efficiency, very high efficiency. That means donor should have own child. Donor should have at least 2 live birth from different IVF conception, like an egg donation. So, and of course, that euploid rate should be high on the donor. So once we select high quality fresh egg donor, also we detect donor spindle, because we have to remove this spindle and throw it away, while 99% of the donor DNA over there. So when we remove and throw it away, we just bring the parent, I mean the female patient spindle, and just transfer into the donor eggs. Then we totally reconstruct the donor eggs. So high quality of the diameter of the donor eggs with good structure, high quality of the mitochondria with the potential energy, and of course 99% your own DNA inside of the donor eggs. So we created totally new structure of the eggs with your 99% of the nuclear DNA. And once this is ready, we are just fertilizing with your partner's sperm. So here there are more technical questions, but I will not go deeply. I will just try to explain simply. So once we take the spindle or pronuclear, doesn't matter, still that will be around many of DNA fragments, because DNA is not just inside of membrane, in all intracellular part containing DNA. But those DNA shouldn't enter into the donor eggs or donor zygote, because they will make many chromosomal abnormality. They will make morphokinetic abnormality, and those embryo will not develop well. That's why we should kill external DNA. So that which we are calling that fusion. So we are making a fusion. We are killing all external DNA, and only your nuclear DNA with the membrane entering into the donor eggs or donor zygote. And then, which we are saying karyoplast, that means we are using that your spindle or your pronicter, which donor egg should accept and should penetrate into the cytoplasm, your spindle or your pronicters. So of course we are agents. So that's I mean, if you are an embryologist, you will understand that very well, because spindle and pronucleus, they are internal cell parts. So even for fertilization with ICSI, intracytoplasmic sperm injection, you know that 5 to 10% of oocytes eggs can be degenerate even with such small pipettes. But we are making here big micromanipulation. So the size of pronucleus even much bigger than size of spindle. So how that oocyte still can survive and will not get degenerate. So of course, secret here is the protocols. So which reagent we are using, then concentration of reagent should be support the oocyte membrane permeability and the cytoplasmic composition, which oocyte will not get degenerate during this micromanipulation. So here I will show the videos how spindle transfer we are doing. As you see over there in the left side, we are finding spindle position. So first we have to determine it. So you will see easily here now, once spindle is blinking over there as a with white color, you will see now. So this is the potential spindle here. So now we detect it, and we need to go to aspirate this spindle. So we are just making a little bit zona drilling with assisted hatching, and then with sharp biopsy pipettes, we are entering into the eggs. This is a female eggs. So we have to female spindle. I mean, this is a patient spindle. We just detect it. So we aspirate it with, of course, some amount of cytoplasm still will come. That's around DNA fragment, which I said we should make a karyoplast and fusion to kill over all DNA. And we will go and we will transfer those spindle into the donor egg. So now we are making a fusion. We are killing external cells. We aspirate back the patient spindle, and this is the donor eggs. Now we go into the donor eggs. We again use laser hatching, and just we are transferring into the donor eggs our spindle. So then we created totally new construction. And the right side, which you see as how your spindle is looking into the cell. So the white one is spindle, as around black one is a cytoplasmic part, but they are also DNA, but we are killing those DNA with some activation. So it is here as a penetration, how cell accepted spindle inside, and then this oocyte will continue to show regular development. So as here as well, you will see much closer and with the zoom how spindle look like. This is with a different mode. You see that spindle is totally visible here with the white color. So we just enter. As you see, the diameter of the pipette is big. That's why I was saying that the protocol is important, which keeping oocyte alive here. Even as you see some morphokinetic, morphologic changes happening. So partially some part of oocyte is coming out, but when you start the work, while I'm doing many of them, so it's not making me worry, because I know that these oocytes after 5-10 minutes will recover itself, and now you will see in video how those oocytes recover itself. So we just enter into the donor egg, we transferred patient spindle. Now you will see soon in a short time how will penetrate, and oocyte will back to, so slowly it's coming back, and right here directly oocyte become in the regular form as the real magic. So when we do meiotic spindle transfer, so when we confirm the mitochondrial mutation, one option is a meiotic spindle transfer. If we have total fertilization failure, because it's happening first meiotic stage of errors, so that's why when we have total fertilization failure, meiotic spindle transfer definitely can be used. If we have confirmed high embryo aneuploidy rate, but which case I said monosomic or high mosaic, but which we cannot help for main chromosomes. So you have to understand that. And low oocyte morphology issue, we are mostly preferring meiotic spindle transfer if we can detect spindle, because fertilization can be risky for the zygote stage with the low quality. If I saw some risk on the degeneration of the oocyte during fertilization, also that I prefer to do meiotic spindle transfer than pronuclear transfer. So how pronuclear transfer is working? The pronuclear transfer, we are working with the zygote stage. That means the day one stage of the embryo development. So we are fertilizing patient X with the partner sperm and at the same time donor X with the patient partner sperm. So both should be in the same stage. Once after, let's say, development finish 18 hours, first stage of development. On the zygote stage, we just aspirate the two nucleus. One nucleus is coming from female, one nucleus is coming from male. So we are just aspirating them and throw away, aspirating them and to put inside of uh, karyoplast for fusion. And then we are going to doing same things for the donor zygote, but in this time we have to throw away donor nucleus because one is coming from donor, one is coming from partner, but still this is a donor DNA. That's why we throw away. And then we are going to back to karyoplast to take out the nucleus, which we killed around of the nucleus all DNA, external DNA, and we just bring them and transfer into the donor zygote. So then we create again reconstructed zygote with 99% of your DNA with your partner and 1% of donor mitochondrial DNA. And this is here how this is working. So as you see, the diameter of pipette now is getting much bigger because nucleus is big. So we are aspirating the both nucleus here from the patient X. You can say that this looks like more traumatic than spindle. Technically not, because both of them are after the penetration, both of them are coming to same form. Just the advantage of pronuclear transfer, this is a ready material. So you know that already it's fertilized. You know that already has a potential for embryo. So the spindle transfer still not fertilized. So that's why there is an issue. So once we get nucleus here, we have to do fusion. That means we have to kill the all external DNA, and then we are transferring into the donor egg with viral envelope protein. So I will share several cases because most of the cases can you see that similar for your cases, so that our experience from the different. So the first case is from China, 38 years old. So which we detect, patient had already detected like syndrome with six major eggs which we received. So already patient has sick child, unfortunately, and we use spindle transfer. So with one euploid blastocyst transfer, and patient give healthy boy, actually in already now 4 years old. So case two again from China. So she has been diagnosed with low ovarian reserve, actually 11 IVF, and only 2 times they had a day 3 embryo transfer, so 2 major eggs, and which use again spindle transfer with one euploid blastocyst, which patient give healthy boy as well. So another patient, 39 years old from US, so 6 IVF trial, 4 major eggs, 2 euploid blastocyst transfer, and patient give birth. So one thing you have to see here, so that definitely we are doing firstly we are recommending strongly, so all embryos which you received from mitochondrial transfer definitely should be PGTA tested. And the critical issue here, how we are selecting patient for mitochondrial transfer, as you see, either they should have diagnosed with mitochondrial disease, either they should have at least 3-4 IVF trial without receiving any embryo transfer or blastocyst. So this is the most critical. So the one, the comparing other cases, 46 years old. So again, low ovarian reserve with 8 IVF trials without an embryo transfer with 2 mature eggs and pronuclear transfer. So patient give also birth. So as you see, even with the low number of eggs, there is possibility. But of course, we prefer to increase number of eggs always. While this is not because we want to work easy and to get blastocyst for easy way. No, but here is the point: we need euploid blastocyst. So more number of the blastocysts we test, we increase the chance much more for the euploid rate. So different cases from UK, 47 years old. So 9 IVF trial before. Again, that healthy child here. So polycystic ovary syndrome, 32 years old. I know this patient very well. So whatever we try, all techniques, all lab techniques, still we couldn't receive blastocyst. And she was giving a lot of eggs, as you see, 21 mature eggs. And even we couldn't get single blastocyst, poor blastocyst, just to have an option for embryo transfer. But on 6 IVF, even 3 of them I involved. I mean, by myself I worked, but I couldn't get from her any blastocyst. And finally, with spindle transfer, 8 euploid blastocyst, which is incredible, and also patient give a birth. So as you said, examples for the different cases, but very well selected cases. So here is the point: we have to know all patient history very well. We have to understand that exactly, and we have to be sure mitochondrial transfer can help them. So mitochondrial transfer not for everyone, but we have to understand exactly this is a solution for your case. So some results about the mitochondrial transfer. So age group by age group, we have different analyses here. As you see on the fertilization rate, of course, the comparing age, that is normal such difference, but still, even for advanced maternal age, so 85-86% of fertilization rate, pretty good and acceptable. When we come the blastocyst rate out of fertilization, so as you check all publications, the documentation, the different journals, different statistics, so to find out from 41 plus 51% of the blastocyst rate is impossible actually. And even the much more interesting, like over 41 plus years old, but still we are getting 63. Of course, this is because of the number of cases, but 63% of euploid rate, like it's very difficult to catch with regular IVF. I mean, also difficult to catch regular IVF uh, blastocyst rate of 51 with 41 plus. It's almost impossible because I'm also working with the regular IVF cycles. I mean, I can say realistically this number for 41 plus 25 to 30%, not more. And if we come to euploid rate, you will find maximum 30%. So here, that means the morphokinetic is very important for embryo. So while morphokinetic development is getting better, so euploid rate is increasing somehow, but still the mechanism is unknown. It's very difficult to detect, analyze, and to make even research for that to find out. Because to make mitochondrial measurement, mitochondrial activity measurement is not that easy, very complicated, uh, very expensive, and also few people only actually working on it. If we check for the clinical pregnancy, of course, 30-35, comparing that advanced maternal age, young age group give very high clinical pregnancy rate. But still, even for advanced maternal age, that means from every 10 cases, 4.5, like around half of them are getting still pregnant. Of course, the live birth rate, uh, comparing clinical pregnancy rate, of course, it dropped a little bit for 41 plus because of different reason, for mostly for endometrial and immunological reason. So abortion rate getting a little bit higher, but this is not connected for embryonic. That is not early stage of abortions. So actually, this is mostly can be immunological or the endometrial factors. So here, as you see, for H by H as a graphic, how that shows for development on the fertilization for day 3 blastocyst and euploid blastocyst. And finally, which is important for us, which we should focus on, is the ongoing pregnancy. So ongoing pregnancy means we didn't lose any pregnancy on early stage, so the pregnancy is continue well. So for each group, so we are keeping over 40. That means they will mostly end up with live birth. So here you can see the diagram how you plot the rate for the different age group. So the mostly when age group get over 40, 45, of course, that as you see, that is more euploid diagram, but mostly we are keeping on the 50% range. So that means still better morphokinetic is affecting the also the euploid rate with the better way. So here that the number of oocytes as a number by number, how efficient for the PNT. You can see separately just for PNT. So as you see, the degeneration rate. So it's a very low, almost like 1.8%. The maximum we get 3.1%. That means maybe an oocyte stage. I even can't remember when I saw the last time degenerate zygote or oocyte. It's very low possibility actually. So, and as a conclusion, so mitochondrial transfer technique can be used firstly for mitochondrial diseases because only the cure or treatment for mitochondrial diseases at the moment. So mitochondrial transfer technique can be used for low ovarian reserve or poor outcome after the IVF treatment because of the better morphokinetic development, because of the better energy source, and also higher euploid rate. And chrononuclear transfer and spindle transfer are the most affecting mitochondrial transfer technique because I heard from many patients about cytoplasmic transfer, polar body transfer. I will be honest with you. So I am partially, of course, I am doing that in a background, a lot of research we done. So the technique is not going like this to go laboratory and take like the microscope and the equipment and work, but background there are a lot of trials and for the different way. So just like I'm openly saying to everyone, like don't spend your energy, your money, your time for cytoplasmic transfer. It definitely doesn't work. So there is no even single reported live birth. So it's just, as for me, waste of time and money. So mitochondrial transfer require good culture protocol and practice of micromanipulation. That's why limited number of people are doing mitochondrial replacement therapy. Of course, one side due of legal issues for different countries, but still it's so much dependent on the protocol. So the honestly, like when I start to make this protocol, I'm saying that probably I'm going back for my time in Australia. I'm at least 5,000 mice eggs for easily I made them degenerate during the practice because I have to find the right protocol, right composition, right molarity for each media. There are different kind of uh, chemicals over there, and you have to establish that microliter by microliter exactly the right amount. Even that 0.01 is making easily degenerate. So that's why it's uh, like protocol and practitioner dependent technologies. So blastocysts which we receive through mitochondrial transfer technique definitely must be analyzed by PGTA testing. So the fusion stage is most important, as I said, karyoplast, because we have to kill out that external part of DNA, which is around of the membrane. So donor oocytes here is very important. So donor should be very well selected and donor should be very well analyzed. So should have very high efficiency, should have young age. Again, donor should have child and also that should be approved donor as number of live birth and also with own child. So, and for the, of course, from part of spindle, if we are using spindle transfer, so that the lab and equipment should be well established with all necessary equipment and technologies. Thank you very much.
Thank you very much for this amazing presentation. I say that because you've got quite a few questions, and I know time is pressing. So for those who ask questions, and if you cannot go through all of them today, Birol kindly agreed to answer those questions offline by email. If I may start, Birol, by asking some of the questions that came in earlier on, how do you select the egg donors for mitochondrial donation? Is it by age, ethnicity? Do you screen the eggs for aneuploidy by NGS screening? Do you need to check blood types and so on?
Yeah, of course. First of all, we have one site recipient, so which we will use mitochondrial transfer. So which we will use mitochondrial transfer. We are controlling their phenotypical information. Of course, that donor phenotype will not shown after the reconstructed embryos or child from the mitochondrial transfer, but still we are taking care of the blood group, especially Rh factors. So also donor has all testing. Even most of the donor we are taking care of, they have carrier screening. So we are avoiding all possible risks from donor. So actually, this is the key point of successful mitochondrial transfer.
Perfect.
But we are giving sometimes chance to patient. I mean, if they wish to select the donor, so even they have this possibility to select, of course, which donor they want. But here, like more than phenotypical selection, we need to know more about efficiency and the genetic potential of the donor.
Okay. Thank you. And another question is it true that only fresh donor oocytes are used for mitochondrial replacement? And I think that is linked with another question asking about the success rate if you're using frozen eggs, whether or not the freezing the eggs and thawing and then freezing the embryos for PGT, awaiting the results and transfer has any effect on the success rate, whether or not you have any
So
experience on
here,
comparing.
patient egg or zygote can be frozen or fresh. It doesn't matter because we will not use structure of the eggs from the patient. But the donor eggs definitely should be fresh. So we don't use the frozen donor eggs. So that we are synchronizing donor day of mitochondrial mutation. Either patient have fresh egg pickup. So we are synchronizing donor in the same day should have egg pickup. If patient has a frozen zygote or eggs, so they are sending from different countries because they need to collect more number of zygote or eggs to increase the chance. In this case, we are just preparing egg donor as a fresh the day of thawing of zygote or their eggs, and then we are making a mitochondrial mutation on the fresh stage.
Yeah. Thank you. There are one or two questions that came through asking, a patient who had multiple failed IVF cycles, having a good number of embryos, but then embryos fragmenting from day 2 and failing to reach blastocyst stage. And patients are asking whether or not they'd be good candidate for mitochondrial replacement.
I mean, of course, that here the cleavage arrest issue that is uh, mostly connected with mitochondrial energy, but of course not always. And to detect this, not easy. I mean, I will say honestly, like if I am sure every advanced maternal age has a mitochondrial energy issue, no. But there is no alternative to give except of this for the advanced maternal age. So that's why I say the number of IVF trial is very important. I'm checking their lab history. So they made the 3 IVFs. All 3 IVFs end up on day 2 with high fragmented embryos, no day 5 blastocysts. So then, yes, they are definitely right candidate for mitochondrial replacement therapy.
Okay, thank you. The other question is studies showing that current studies showing like mosaic and segmental embryos can lead to healthy babies. And do you transfer if you reconstruct an embryo and you find it mosaic or segmental? do you have an opinion whether those embryos would be considered for transfer in those instances based on the current
So
data
yeah,
results?
mosaic embryos still a big discussion
Mm.
between everyone. So actually, till 50% of the mosaic rate uh, still, I guess, is available for embryo transfer, and we are transferring because we have to understand that those patients are receiving those blastocyst rate. I mean, number of blastocysts very difficult way. So to lose those potential of blastocysts, even if they have very high morphokinetic. So of course, we are using this chance to transfer because we have to think about the blastocyst completely. We are taking that only 3 cells from trophectoderm we analyze. So those 3 cells give 40% of mosaic, and if we like a thought all embryo has same potential, that will be a mistake. So that's why the main question now about pgt, because we are getting local cells, and uh, about these local cells we are completing all embryo as aneuploid or mosaic. So partially aneuploidy is a risky because everyone asking healthy baby. They want to have healthy baby. That's why for aneuploidy we are more strict. But for mosaic embryo, and my experience, I had even with 50%, 60% mosaic rate who give a live birth. So there are examples. There are many studies also which shows that mosaic embryos can give. But if there is high percentage of aneuploidy, even with the special number of the chromosomes, of course, there is no chance to transfer this embryo.
Another question, why do you transfer the nuclear DNA to the donor egg and not the mitochondria from the donor to the intended mother egg? I think,
Mitochondria is
yeah,
everywhere. Mitochondria is not, you can detect by even some technology or transfer, because mitochondria is not like only you can detect with electron microscopes. So, but which is not available, you can aspirate mitochondria and to put in the another cells. So that is not possible, technically impossible. So that's why only way we can transfer to nuclear DNA. I wish that we could do mitochondrial DNA, so it would be more easier, of course.
thank you. I think this is a comment turned into a question. There's someone asking about exercise usually recommended to build up mitochondria in during through sports and cold showers and so on. And one patient is asking whether or not that could sort of continue into the sort of health of the eggs in terms of its mitochondria. Do you have any opinion on?
So again, I'm saying that mitochondria is all around of body. All part of our body has mitochondria. So some of them are extracellular, some of them are intracellular. So of course that your habits with your genetic, with what you are eating, how you are living, you are smoking, you are drinking. So all of them uh, will affect that the mitochondrial function or dysfunction. But intracellular mechanism, things are not going exactly like this. So you can do physical activity. It can help to you to supply for your body more energy. You can feel much better. But from the intracellular stage, you cannot increase your egg quality with that. You cannot increase the potential of your mitochondria into the intracellular mechanism on the egg. That will make a miracle. So, of course, those things will affect your body with a different way. Your endometrial receptivity may influence from that. Your metabolic mechanism and follicular development may influence right way. But on the intracellular mechanism of the egg, actually, of course, not possible to measure this effect, but it's not so much connected.
There's one or two questions asking whether or not the future effect of those technique on the children born.
So
Do
the
we have?
yeah. So the first child who was born from this technology already 14 years old. So it's already a long time to go. And mine, I will say that I have first child already now 7 years old. So we have a 23 live birth already, and I didn't heard from anyone any issue like health issue. Uh, from one side, you are doing, let's say, egg donation. Let's say not even IVF, egg donation. So no one knows this donor has mitochondrial issue, yes, because you are just selecting from one bank, you are buying egg and you are making transfer. Even for yourself, you are doing IVF, but you don't know you have mitochondrial issue, mitochondrial mutation, or mitochondrial disease, like you are doing. But with the mitochondrial transfer, donor is well selected. So we know that donor has healthy child, donor has healthy live births from the different IPs, and they have healthy child. So obviously much more sure way to comparing egg donation, even regular IVF, to get healthy baby from this technology than others. So of course it's very, very low possibility. I'm not saying about the morphological issues during pregnancy. Some morphological issue can be happen, which is not chromosomal because we are testing with PGTA, which is not connected with mitochondrial disease, but some morphological issue if happen, this is on one side. But I don't have any information. There is no any even single publication which shows that from mitochondrial transfer baby was born with the genetic disease or uh, mitochondrial mutation.
Okay, thank you. Um, what percent of eggs from patient over 45 are diploid when using MST? I think the question is because of the link between mitochondria and aneuploidy. Is there a data to if you do that transfer that the rate of aneuploidy reduction?
So I can say that the most of the cases which are coming to us, of course, they have unemployed issue. But I mean, mostly we are selecting patients which they don't have any blastosis, so that's why they don't have unemployed issue because they don't have blastosis. But several number of patients which had never euploid embryos, always they receive unemployed, but the blastosis, but always end up with unemployed. So I can't say that all blastocysts we developed from them euploid, but we give them chance at least one embryo transfer for the euploid embryos. So because those patients doesn't have issue with the implantation or pregnancy, those patient has an issue, they cannot find the healthy embryo to transfer. So once if we get even one euploid, to potentially it's a pregnancy for them. So that's why of course helpful, but again I'm saying those patients mostly had uh, different aneuploidy issue. Like, for example, they were transferring that, they were sending that PGT embryos with the 4BB, 4BC, like a low quality of embryos. And they were coming aneuploid, but which we created with the mitochondrial transfer as a 4AA, 5AA, like a comparing very high quality. So we got for them at least one or two euploid blastocysts for the transfer.
Yeah, I think there was another question. And typically, how many zygotes do you need to reconstruct to obtain a euploid live birth? Typically, is there a recommendation about the numbers?
So actually, like I'm suggesting minimum to get six. So because the aim at least to give them chance for two embryo transfer, at least two blastocysts, euploid one, to get two chance, because there are two reasons for that. I mean, I see that from our patients mostly. Whoever get the first child, they definitely want second one. So that is at least one more option for second embryo. Or if they have at least two blastocysts, and if first attempt get implantation failure, sometimes it's happening, so for them at least one more hope. So that's why the more number of eggs or zygotes is increasing chance, but I can say six is at least minimum, six is ideal to get at least two euploid blastocysts to increase the chance for embryo transfer and implantation.
Perfect. Um, we're getting close to 8 o'clock, but so do we take one more question? Would that be okay? You mentioned 99% of the DNA. What of the mitochondrial DNA is transferred? What happens to the 1%? There's one question. To the 1% of the
So
DNA.
1% is of the DNA is the mitochondrial DNA of the donor.
Yeah.
So this
Yes.
is obviously will be from the donor. So once do NIPT test or real-time PCR, that's why they are calling that. I said on the beginning of presentation, three parents baby, because they will easily detect three different genes. So that is very funny, like a story we made a mitochondrial transfer and patient going to NIPT, and lab called me from the genetic lab because they didn't know probably patient has a mitochondrial transfer, and they said, oh my god, there's very interesting issue, but this patient has three different genes, how it can be possible, and which is the right one we have to focus on. So uh, that is the percentage of mitochondrial DNA, how it may affect, but this is not for regular DNA fingerprints that they can find three different genes, but with NIPT and the molecular level of the uh, microarray, yeah, they can find out.
Thank you very much. The questions are still coming in. There's quite a few. Uh, Apologies for those who sent the questions and we couldn't answer them, but what you will receive is a contact email about how you can contact us too, and you will receive the replies. So hopefully from Birol, we'll be able to review them at some point in the very near future. For now, I want to thank you again for this excellent presentation. Very, very interesting, very thought-provoking.
It's my pleasure.
We look forward to the next session, hopefully in the next month, and the next topic in the series of on this replacement therapy. Good evening, everyone.
Good evening.
Thank you.